So the title of this video is Prospect of Solar Photovoltaics in BC. However, this presentation is applicable to any regions with a little change in numerical figures through slides 24 to 33. As the price of the solar panels are coming down year over year, it is increasingly becoming more and more popular in many parts of the world. Places where there are more sunny days over the year, it has already become a financially viable project. I'll discuss various issues including the financial aspect of a small-scale solar photovoltaic project in BC. I'll first start with how a solar cell works. A solar cell is a large silicon device, basically a large PN junction diode with a very thin top layer, that is N-type layer. When light is incident on a solar cell, photon particles knocks off electron. These electrons are caught up by the electric field in the PN junction region. Electrons are deposited on the top layer and the holes on the bottom layer. Due to this charge separation, a voltage is created. For silicon solar cell, it is around 0.6 volt, and the current depends on the intensity of the sunlight and the area of the solar cell. Brighter the light, higher is the number of electrons, and larger the area, larger the number of electrons. Characteristic of a solar cell is very different from that of a battery. It acts like a constant current source up to a certain range, and then the voltage drops drastically. Usually for silicon solar cell, the maximum voltage available is around 0.6 volt. With the intensity variation, this voltage variation is very little. What changes is the current. Higher the intensity of the light, higher is the current. When several solar cells are connected in series, the voltage is added. For instance, if 3 solar cells are connected in series, then the total voltage at the terminal of the series combination is 0.6 multiplied by 3, that is 1.8 volt. And when, for instance, 3 solar cells are connected in parallel, the voltage at the terminal remains the same, 0.6 volt, however, the current is tripled. A solar panel consists of many solar cells connected in series. For instance, a 72 cell solar cells connected in series, the voltage will be 72 multiplied by 0.6, that is 43.2 volt. We are taking a solar cell and light is allowed to shine on its surface. The terminal is connected to a variable load. If the load resistance is very low, the current is almost the maximum current, but the voltage across the load is also very little, so power dissipated by the load is V multiplied by I, that is also little. As the resistance goes higher and higher, the power dissipated by the load becomes higher and higher. But beyond some certain point, as the load resistance increases, power also starts to decrease. So there is a maximum power point beyond which the power starts to decrease. So our intention would be to adjust the load or adjust something so that the load always gets maximum power out of the solar cell. And this maximum power point, it does not remain fixed. As the intensity gets brighter and brighter, or intensity gets dimmer and dimmer, this also varies. There are three different types of solar cells mainly found in the market. One is called monocrystalline. The efficiency is 20% or little more than 20%. And polycrystalline, the efficiency is around 15%. And then the third category is thin film. The efficiency is around 12%. Price also varies. Monocrystalline is the most expensive one, then polycrystalline, and then thin film. Let us now consider a typical photovoltaic panel characteristic. For instance, LG model number LG390N2TA5. Each cell dimension is 16.17 centimeter by 16.17 centimeter, and there are 72 cells in the panel. The maximum voltage available, that is 49.2, and maximum current 10.15. However, as we have shown earlier, that our goal is to bias a panel at the maximum power point, and if it is biased at that very point, then the voltage we find is 41.4 volt and the current is 10.1 amp, and so the maximum power we can get from this panel is 390 watt. Whenever we are talking about the power available from a solar panel, it is always under standard test condition. And what does it mean? That 1 meter by 1 meter square. Usually at noon, the sunshine is around 1000 watt per meter square. It varies, of course. In the equator, it is more than that, and in the polar region, it is less than that. But in average, you can consider to be 1000 watt per meter square. So in our typical LG panel, we get 390 watt under standard testing condition. So surface area is its length by width, that is 2.11 meter square, and the peak solar density in peak solar power on the incident on the panel is 2.11 kilowatt. So the panel efficiency can be easily found, that is 390 by 2110, that is 18.5%. As before, if our LG panel now is exposed to sunlight and we are connecting a load, we can find, as the load varies from low to high resistance, we can find that at maximum power point, the voltage is 41.4 volt and the current is 9.43 ampere, and the maximum power represented by the entire region, that is 390 watt. Now, if this panel output is connected to a battery, it is a 12 volt auto battery, what happens? In the middle of the charge, the voltage across the battery is around 13 volt. When a battery is fully charged, this voltage becomes 13.6 volt. Let us consider that it is in the middle of charging, and the terminal voltage we are getting is 13 volt. Then the current through the battery, that is the charging current, should be the maximum, that is 10.15 amp. So the power going into the battery for charging is 10.15 into 13, that is 136 watt. Now you can see that the panel can give 390 watt, but we are using only 136 watt. The rest 254 watt is unutilized. So how can we utilize the entire power? So we can utilize the maximum available power from the battery by using an electronic circuit that is called MPPT, or maximum power point tracker. What it does, it biases the panel exactly at MPP under all circumstances. So now, after the MPPT, we are using the battery for charging. In this case, what happens that the panel is biased at MPP, so entire 390 watt is utilized for charging the battery. But the battery voltage is 13 volts. What happens is that the current is increased several times. So the battery will be charged this time much quicker than before. Most of our household appliances need 115 volt AC. So to run our household appliances by the photovoltaic panel, we need first MPPT so that the panel is always driven at the maximum power point. Then a charge controller which controls the charging of the battery and discharging. And then we need an inverter which inverts the DC into AC, and this AC can be utilized by your appliances then. If we install a large number of solar panels on roof or any open space, and we are using solar inverter, the output we are getting AC, and we can utilize this AC in home, or we can sell it to the grid, and whenever the power is needed we can buy it back from the grid as well. So for a grid connected photovoltaic system, what we need a large number of solar panels, then combiner box, then the disconnect connect switch, and the solar inverter, circuit breaker, and then it goes to the grid. A grid connected solar inverter does many things simultaneously. It is not an ordinary inverter. It has a maximum power point tracker which ensures that the maximum power available from the PV array is utilized, then the inverter, and then the PV inverter controller. So it is always tracking the maximum power point and bias the panel exactly at the maximum power point. And another thing it does, that is called grid synchronization. It delivers current to the grid when in accordance or in synchronism with the supply voltage.